Hello everyone and welcome to the channel. Are you still managing static SSH keys that never expire? Static SSH keys have been a headache for years. If a key is lost, stolen or shared, your system is wide open for attack. What if I told you there's a way to make your SSH access more secure and simpler using short-lived certificates with Cloudflare? Cloudflare replaces static keys with short-lived SSH certificates. You authenticate through Cloudflare Zero Trust platform, and your authentication window is time limited, and your access is verified in real time. In this video, I will walk you step by step through securing your SSH servers with Cloudflare, how short-lived certificates work, and why this approach is a game changer for security and operational simplicity. Ready to upgrade your SSH security? Let's get started. In a traditional SSH key-based authentication, you generate a key pair, a private key and a public key. Then you add your public key to the target server's authorized key file. And that's it. You can now log in without using a password. Not to get into much detail, the private key lets you sign data, while the public key enables you to verify the signature. This allows you to verify the integrity and authenticity of a message. In SSH key-based authentication, the server generates a challenge, that's some random data, and sends it to the client. The client signs the challenge using its private key and sends it back. The server then verifies the signed challenge using the public key stored on its side. This confirms the client authenticity, as only the client having the private key can generate a signature that matches. Mind that no passwords or keys are sent over the network. While this method is secure, it comes with several drawbacks. The keys are static and do not change. If a private key is lost or stolen, an attacker can gain access to all servers where the key is used. Moreover, rotating SSH keys is cumbersome and time-consuming. You would need to log into each server individually and replace old keys with new ones. If a key is compromised, revoking it is also challenging. You would need to log into every server, locate the key and remove it manually. This process requires maintaining an up-to-date list of all servers and accounts where the key is stored. That task is not manageable at scale. Instead of relying on static SSH keys, a much better and more secure option is to use short-lived certificates. Let me explain how it works. We start by creating a key pair that will act as a certificate authority, CA for short. This key will be used to sign user SSH keys. I will run SSH keygen to generate the CA key pair. Let's verify that the keys were generated. Now, let's display the public key so we can copy it. Next, we configure the target SSH server to trust certificates signed by our CA. On the target server, I will create a file for the CA public key and paste the content of the CA public key into it. I will set appropriate permissions for the file. Now, I will update the SSH server configuration to trust the CA and restart the SSH service to apply changes. On the client machine, I will generate an SSH key pair for the user. Now, we use the CA private key to sign the user's SSH public key. This generates a short-lived certificate. We'll specify -s to use the CA private key to sign the key, -i to specify the certificate identity, -n to specify the SSH user the certificate is valid for, -v to set the certificate validity to 5 minutes, and finally, we'll provide the path to user's public key. A signed certificate has been created. Let's test logging into target server as user 1. We are in. Notice there's no authorized key file on the server. The SSH key was trusted because it was signed by the certificate authority. Now, let's try connecting as user 2, who was not included in the certificate. It fails, as expected. Let's check the authentication logs on the target server to confirm. Short-lived certificates automatically expire after their validity period. Let's try reconnecting as user 1 after 5 minutes. Access is denied because the certificate has expired. Let's check the logs to confirm. Short-lived SSH certificates offer a more secure and flexible way to manage SSH access. Each certificate can specify a list of valid SSH usernames as well as host names it can be used for. This ensures that even if a certificate is valid, it can only grant access to specific users and servers. Additionally, SSH certificates have a defined expiration time, limiting their duration, and can be revoked when needed. Let's see how Cloudflare Zero Trust fits in. We have two Linux servers, Node 1 and Node 2, both of which will access using SSH. Each server is running Cloudflare D, a lightweight daemon that establishes a secure outgoing tunnel to Cloudflare's global network. While Cloudflare D is commonly used to expose HTTP applications to the internet, in this scenario, we'll leverage it to enable SSH access to a private network. Both servers have user 1 and user 2 accounts set up. On the client side, we have two Windows machines, one for user 1 and the other for user 2. These machines are running the Cloudflare Warp agent, which creates a WireGuard tunnel to the Cloudflare infrastructure, allowing secure connectivity to the servers. With this setup, clients can securely access the servers via SSH, with all the traffic tunneled through Cloudflare's network. The servers do not require a public IP address or have their SSH service exposed to the internet. Instead, the SSH traffic reaches the servers through the pre-established Cloudflare tunnel. This covers network reachability. Both the servers and the clients are connected to the Cloudflare infrastructure. Let me do a quick demonstration. I'm on user 1 Windows machine and I will SSH into the Node 1 server as user 1. Okay, I'm in. Now let's try connecting as user 1 to the second server. That's Node 2. That works too. Next, let's switch to the second Windows machine owned by user 2. I will SSH into the first server, that's Node 1, works perfectly. Then let's SSH as user 2 into Node 2, that's the second server. And we are in. At this point, you might say, alright, you just show us SSH connections over a VPN, and now it looks like you are demonstrating SSH public key authentication. What's the big deal? Stay with me. Let's dig deeper. I will list the files on the first Windows machine. Let's navigate to .ssh folder. There's no SSH key pair here. The only file present is known hosts, which holds the public keys of the remote servers. Let's connect to Node 1 and check the files there. No authorized key file. In fact, there isn't even a .ssh folder. So, how is this working? Let's try connecting again, but this time I will enable verbose mode to see what's happening behind the scenes. Aha! The authentication mode in use is none. That means no authentication is being performed. So, let's test one more thing. I will try connecting as user 2 on the first Windows machine. And this time, access denied. So, how is that when I SSH from user's 1 PC to user 1 on the server, I can log in without providing any credentials, yet when I try to connect as a different user, access is denied? Let me show you how this setup is wired, because it's really clever. And no, it's not using an authentication agent. As you already know, user's 1 machine is connected to the Cloudflare network via the Warp client. If we take a look at the Zero Trust console, we can see not only the Windows machine, but also the user who enrolled the device. The user is identified by their email address, which is then associated with the device. This email is what allows us to configure access permissions for resources and applications within our Zero Trust environment. Now, let's check the second machine, which belongs to user 2. It's also connected to the Cloudflare network. In the Zero Trust console, we'll see users to device listed as part of the Zero Trust domain and associated with the email user2@linuxcloudhacks.ovh. I will show you later in the video how to register a device with Cloudflare and associate a user with it. Next, let's run a warp CLI target list command on user's 1 machine. This will display a list of available SSH servers along with the SSH usernames that can be accessed from this device. From this device that's registered to user 1 Linux Cloud Hacks, I can access Node 1 using user 1 SSH login and Node 2 using user 1 SSH login. If I run the same warp CLI target list command on user's 2 machine, the results are different. From this device, as user 2, I can access node 1 and node 2, but using users2 SSH login. Let's take a look at the Cloudflare console under the Access section. Here we can see that two services are exposed. Let's inspect the details for node 1. The target is node 1 server, the destination port is 22, and the service type is SSH. The concept here is similar to exposing an HTTP service, but this time we are exposing SSH access. In the Policies section, we define who can access the service. Let's take a closer look. If I select the policy named user1, it specifies the email user1 Linux Cloud Hacks OVH can connect as SSH user1. If I select the policy for user2, it allows the email user2 at Linux Cloud Hacks OVH to connect as SSH user2. Now, let's edit the user2 policy and add user1's email to include section. This means user1 Linux Cloud Hacks OVH will now also be able to access SSH user2 on the node 1. Let's save the policy. Back on user's 1 machine, let's rerun the warp CLI target list command. As expected, the list has been updated and we can now SSH into node 1 using either user 1 or user 2 accounts. Let's test it. I will SSH into node 1 as user 1 and it works. Now let's try logging in as user 2 and that works too. With this model, you can centrally manage your SSH access policies. You simply define which users can SSH into which servers under which SSH usernames. If you need to revoke access for a specific user on a specific server, there's no need to log into the server to remove the keys or change passwords. Instead, you can easily manage it from the Cloudflare console. You might wonder how this works, given that there's no certificate stored on the client. Here's the process. When you attempt to SSH to a server exposed as Zero Trust infrastructure application, Cloudflare intercepts the traffic and routes it through its SSH proxy. The proxy leverages the client's already authenticated identity via the warp client. Then it validates the user identity against configure policies to determine if access to the target user and server is allowed. If the policy deny access, then connection is immediately rejected. However, if the policies permit access, the SSH proxy generates a short-lived certificate signed by Cloudflare's SSH certificate authority and presents it to the target server, granting access. As for the connection between the client and the SSH proxy, the authentication type is set to none, meaning the client doesn't need to authenticate itself to proxy again, as Cloudflare has already authenticated the end user through the warp client. In short, the client connects to Cloudflare SSH proxy, and the proxy connects to the target server on the client's behalf. Let's get everything set up. There are a few prerequisites to cover first. You will need to register with Cloudflare Zero Trust, which is free for up to 50 users. While not mandatory, in this video we are using our custom domain, Linux Cloud Hacks OVH, along with Google Cloud Identity free tier. Now, the setup itself is divided into 5 sections. 1. Connecting servers to Cloudflare network. In this section we'll use Cloudflare D to link our servers to Cloudflare infrastructure. 2. Configuring Cloudflare Certificate Authority. In this section, we'll set up Cloudflare CA and configure servers to trust certificates signed by it. 3. Integrating Cloudflare with Google Cloud Identity. In this section, we'll integrate Cloudflare with Google Cloud Identity using SAML. 4. Registering client machine. In this section, we'll register client machines using Warp software. 5. Exposing SSH services as Zero Trust applications. Finally, we'll expose SSH services on our servers as Zero Trust applications and configure Zero Trust policies. To connect our servers to the Cloudflare network, we have two options: Warp Client or Cloudflare D. If you want to attach an entire network, it's better to use a single node with the Warp Client acting as a gateway. However, if you only need to attach a single server, Cloudflare D is the easier choice. That's what we'll be doing today. First, I will go to Zero Trust, then Networks, and click Create a Tunnel. I will select Cloudflare D and name the tunnel Node 1, since it points to my first server. Next, I will choose Debian64, copy the installation commands, and run them on my server. The server's IP address is 192.168.10.3. Once the tunnel is up, I will click Next. In the Private Network tab, I will add the server's IP address, save the tunnel, and head to Routes menu. Here I can see the route to node 1 IP via node 1 tunnel. Now let's repeat the same steps for the second server. I will go to Tunnels, click Create a Tunnel, and select Cloudflare D. I will name this tunnel node 2, copy the installation script, and paste it into the console of the second server. The IP address of the node is 192.168.10.4. Once the connection is established, I will go to Private Networks tab, add nodes to IP address, and save the tunnel. Finally, in the Routes menu, I can see a second route pointing to node 2 via node 2 Cloudflare D tunnel. That's it. Both servers are now connected to Cloudflare network. Configuring the Cloudflare Certificate Authority is only possible via the API. And to interact with the API, we need a bearer token. First, let's go to Manage Account, then Accounts API Tokens, and click Create a Token. I will choose Create Custom Token, name it SSH, and grant access SSH auditing permissions in Edit mode. After clicking Continue, let's create the token and copy it. I already have an HTTP post request ready to create the certificate authority and return its public key. I will paste the copied token into the authorization header. The only thing missing is the account ID. To get it, I will go to Websites, select my domain, and copy the account ID displayed on the right. Let's now paste it into my request and send it. Success! The CA is ready. Let's copy the certificate authority public key and save it as a file named ca.pub in the etc SSH folder on node 1. Let's also make sure to set the correct permissions for the file. Next, I will open the SSHD configuration file and add these two lines. This tells the SSH server to trust keys signed with the CA public key. Finally, let's restart the SSH service to apply the new configuration. Same steps need to be repeated on node 2. The next step is integrating Cloudflare with Google Cloud Identity. This step is optional since we can authenticate users using a one-time PIN sent to their email. While this works, it's not the most secure or convenient method. A much better approach is to delegate authentication to an identity provider like Microsoft Entra ID or, in this case, Google Identity. I'll start by going to Zero Trust, Settings, Authentication, and adding a new login method. I will select SAML. In the Google Workspace admin console, I will navigate to Apps, Web and Mobile Apps, and click Add Custom SAML Application. Let's name the application Cloudflare and click Continue. I will copy the single sign-on URL from Google and paste it into the respective field in the Cloudflare console. Then I will go back to Google, copy the entity ID and paste it into Cloudflare. Next, I will copy the certificate from Google and paste it into Cloudflare certificate field. I will take the single sign-on URL from Cloudflare, insert the correct team name, and paste it into Google. I will reuse the same link for entity ID in Google and click Continue. In the Attribute Mapping section, I will map primary email to the email address field and click Finish. Next, let's save the Cloudflare setup and return to Google Admin Console. There, I will click Test SAML Login. After allowing access, I will set the service status to On for everyone and click Save. Finally, I will test the integration from Cloudflare by clicking Test. Next, I will enter user's one email address and password. Success! The integration works. Now, I can create users in Google Identity and use them seamlessly in Cloudflare. Let's shift our focus to registering client machines. First, we need to configure who is allowed to register devices in our Cloudflare Zero Trust domain. To do this, I will navigate to Settings, select Warp Client, and click Manage Device Enrollment Policies. Next, under Authentication, I will disable the one-time PIN option as we only want to allow registration via the Google Identity provider. Now, let's head to Rules tab and create a new rule. I will name it Linux Cloud Hacks and configure it to allow only emails ending with Linux Cloud Hacks. Once that's set, I will click Save. From this point forward, Enrolling a new device will require authentication through Google IDP using an account within the Linux Cloud Hacks OVH domain. Now let's move to the first client machine, which belongs to user 1. The Cloudflare Warp client is already installed. I will click the gear icon, navigate to Preferences, then Account, and select Login with Cloudflare Zero Trust. Here, I will enter the Zero Trust team name, which brings up the login screen. I will select SAML, then enter user's 1 email address, and password. Success! The device is now registered with Zero Trust under Users 1 account. Let's connect to the network. If I check the device menu in Zero Trust dashboard, I can see that User 1 device has been successfully registered. Next, we'll repeat the same steps for the second client machine, which belongs to User 2. On User 2 device, I will open Warp Preferences, go to Account, and select Login with Zero Trust. After entering the Zero Trust team name, I will choose the SAML identity provider, then enter user's 2 email address and password. Success! We are in. Finally, I will connect this device to the network. Back in the Cloudflare Zero Trust console, I can see that the second device is now registered. With that, we successfully connected both the servers and the client machines to the Cloudflare network. Finally, let's expose the SSH service on node 1 and node 2 via Zero Trust. The first step is to define targets, which we can reference later when setting up Zero Trust application. To do this, I will navigate to Networks, Targets, and click Add a Target. Then I will enter node 1 in the hostname field and specify the private IP address of the server. Let's click Add a Target. Now I will repeat the process for node 2, entering node 2 as the host name and its private IP address. Once both targets are defined, let's save the configuration. Next, let's make these targets accessible within Cloudflare network. I will go to Access, then click Add an application. For the application type, I will select Infrastructure. I will name the application Node 1 and choose Node 1 as the target. Then I will set the listening port to 22 and the protocol to SSH. I will click Next. Now let's attach Zero Trust policies to specify who can access the server via SSH. I will create a policy named user1. Then I will add the email address for the user, that's user1 at Linux Cloud Hacks OVH, to the policy. Finally, I will specify the SSH user ID for this policy, that's user1. This configuration ensures that only user1 can access the server via SSH after authenticating through Google Cloud Identity. The policy effectively maps Google Cloud Identity user to the SSH account on the server. Let's click Next to save the setup. Node's 1 SSH service is now exposed to Cloudflare network. To add another user, I will simply create a second policy. I will add a policy named user2, then I will put the user2 at Linux Cloud Hacks OVH as the user email that the rule applies to. Finally, I will specify the SSH user ID as user2. This flexibility shows how easy it is to grant or revoke SSH permissions. Authentication is handled by Google and access policies are managed in Zero Trust. To expose the SSH service on node 2, let's repeat the same steps. First, I will click Add an application, select Infrastructure, and name the application Node 2. Then I will choose Node 2 as the target. Next, let's define the access policies. I will create a policy named user1, add the email address, user1 at Linux Cloud Hacks OVH, and map it to the SSH user1. Then I will add a second policy for user2. Set the email to user2 at Linux Cloud Hacks OVH and remap it to SSH user2. And that's it. With these steps, we successfully exposed two SSH servers, Node 1 and Node 2, as Cloudflare Zero Trust infrastructure applications. Granting or revoking access is now simple, secure, and fully managed via Zero Trust policies. So that's how you can leverage Cloudflare Zero Trust to secure your SSH access with short-lived certificates and centralized access control. It simplifies key management, eliminates the risk of compromised keys, and provides granular control over user permissions. If you are looking for a more secure and manageable way to access your servers remotely, then this is a great option. Why not to try it yourself? There's a free tier available for up to 50 users. If you found this video helpful, don't forget to give it a thumbs up, subscribe for more tutorials like this, and leave a comment if you have any questions or suggestions for future videos. Thanks for watching, and I will see you in the next one.